Nekem mint akkor
már is
elkezdem rögzíteni.
Ez nagyon fasz, és ez fönn is marad a YouTube-on.
Igen.
Ez nagyon durva. Baszki. Vigyázzunk, mit mondom.
Megválthatom egyébként.
Hát az ilyen üres részeket, de majd ezt megcsinálják a logikus srácok. Ez a statisztika, vagy?
Nem, ez a... Most nem látjuk, hogy egy screen share van, nem látjuk a többi videót.
A karok.
Kifértél az öreg?
Semmi, csak hogy ezt rakték.
Ja, igen.
Meg hogy...
Jött valaki minden felhozom.
Oké.
Jó reggelt! Nem tudom, már jobban van a között.
Ja, külön rossz. Egyrészt én Balázs. Bocs Balázs.
Képzeljétek egyébként, amikor eltettem a kezemet, akkor megkellettem a járásra a motorjára. Rettenetű szarhely.
Igen, ez ott is sokszor voltam.
Igen, most bementem, teljesen modern vizsgáló, 1 óra alatt végeztem röntgennel, mindennel együtt. 1 óra.
Mert sok a gyerek részén voltam sokszor, és a gyerek részén területen a többfélesülel vett, meg valaki megdobták sok könyvet, és megkerestették, hogy minden előtt, de nem így dolgoztunk. Emlékszem, úgy tűnt, hogy rájönnek valami kisfajta volt, nem nagy, és akkor előtt is megállapodunk, és így ültünk, és így azt néztük az elkóval, hogy a két foglalkozó találkozik. És szemközti oldalon, hogy azon próbáltam megkötni a gyereket hajnali egykor, hogy nézd aranyos.
Amikor összevettek a lábamat, akkor így jött egy ilyen csávó, és így sétálgott az kötécselt, és tényleg elhúzott magad, és egyeség jött egy ápol, azok ne sétáljanék magad tévét is. És akkor tudod, hogy így, amikor az ápoló is felveszi a maszkot, meg a kesztyűt, de hogy most teljesen jó, volt egy ordítozó magával elhúzó csöves, de azzal ők nem tudnak.
Sziasztok! Azzal nem tudsz csinálni, aki a beteg, az beteg. De a környezetet.
Lehet itt foglalni egy fél?
Bárhol.
Őszinte legyek el, és most azt hiszem, hogy 14 éves koromban tudom szólni, hogy igazán még bosszúkorán jelen.
Nem jól mondod, az egészségünk nem szorult rá.
Ja, ugye azért nem láttuk a sarkon, hogy rám kinézelgetünk, így mentős. Na, rész.
Ennyiszer voltam a mutatében, akkor nem 100-szor valami ezt számolni. Hát az autóiművezetések és azért olyan kontrollra járok állandóan.
Én parkoló legyek elfogadó. Csak mondom, de amíg barátig lehet. Van kávé, azt hiszem,
Csak egy kérdésem van.
igen.
Dohányzó van?
Az itt belül sehol nincs, oda lehet kimenni a parkolóba.
Én csak kijön, csak visszajönnék.
Ez egészséges.
Hát, hogyha van esetében akkor az osdiba kell menni. Senkit nem érdekel, hogy nem oda hagytak be, ott van, hogy próbáltuk. Hát az túl, az amerikai.
Az amerikai út az
Van
lehet.
nem, azt szerintem az amerikai út volt. Az ott ez a energiét, Azt biztosan csinálták.
Igen.
internetet valahogy felválni.
Nem olyan szükség, hanem ugye akkor a mágnesesség van benne, hogy nem kell csinálja a képeket, mozdul. És akkor megnézed a YouTube-on ilyen képeket, amikor a gyerekek elfelejtik a palacot az energiát. És így a szupravezetőkben sarokból berállítja. Iszonyat sok olyan baleset van, ez egy tipikus ember baleset, hogy kis rögzítve a palack a sarokba, és akkor bekapcsolják a mágnest, akkor berállítja a palackot, lelőjük a szelepre, és 200 bármi jelenik részébe így a betegnél vagy valahol, és hogyha hangzik, akkor végszalak lesz.
A kémiások a legjobb, hogy kémiásoknál ugye van az első egy nagy energia, aminek ilyen külön izéje van, külön szerkezete van belül az épületben, ugye kompenzálja a rezgéseket. Még 2 vagy 3 éve már ide járt, az egyik kémiaprogram, nem felejtette a kis fénykorodat. Valami 20 milliós kárekkor gondoltál benne verben. De nekem ez a legnagyobb tény, miért is az nevelében az emberben. Az emberek félnek a nukleáris.
Nem én azon gondolkodom, hogy milyen lehetőek, amikor van az a sztori, hogy amikor csatlakoztunk az alig, amikor én csatlakoztam az alighoz, nem, hanem hogy volt nekünk a listortak és a csatlakozásunk, amikor érdekelünk, akkor az első feladatom az az, hogy a mágneses tereket lehetne írni amikor az üres mágneses. És így van az a régi filmszerszínűsában, amit ki kellett nézni, az megint olyan bronzból, és az összes eszköz bronzból, amit benne van.
Igen, az nem más esetben.
Újra elmondani, hogy mit tűnik, hogy az arcán benne van a kicskára a bőrjében, és hogy benne között akkor javta, de mágnesesség az volt, féltesztában nem játszott. És akkor utána az volt, hogy az eszközök meg tök jól lehetett mindent használni, kivéve volt ilyen cicalékből, tudod, ez a három akármi is. És a lapjaiban voltak hívak, de azért elég nagy volt a felület. És amíg leraktad, addig oké, de amikor mozgatod, akkor Lorenz elrúgik a sarokból. És így nagyon durva volt, hogy meg kell minden kevesebb örvényáron keletkezzen. És így az volt, hogy megfogtad a széket, és így alékottad, érezted, hogy mit húzik, de ha egy ilyet csináltál, akkor csináltad egy ilyen rossz széket. Azzal játszottunk, és így azt szerint, hogy mentek, hát mindegy, be nem mentünk bele, vagy legalább nem ügyeskedtünk, meg kint a ujjomfal és a mágnes között van egy ilyen relatíve nagy rész, ahol lehetett találhatatlan emberrel küzdeni, és így az volt, hogy megfogtad a lábát, így rágulod, és jobbra volt neki. Nem, ez az volt, hogy tudtam, hogy neki is bekamerálsz valamit. És így hajnalban, amikor a mágnes, mindegy, volt egy olyan rész, hogy a mágnes szkennelt, és akkor át kellett fordítani, és utána át kellett forratoztatni a másik végére. Ez egy ilyen 1000 bosszondából álló ilyen valami volt, amit egy ilyen sima mászkál. És akkor az volt a feladat, hogy ez magától nem, 1 óra alatt végig, és utána elején kellett rakni ez óra, ami feladatunk. Igazából meg az adatunk. És hát amíg így vonatozott át, azt is persze mordalasra csinálta, és azért vagy így mentem munka. Ez 53 7 perc.
Vékát azt ismeritek azt a filmjelentéseket.
Pakistan is
Amikor az egyik srác nem fogalmítta, kijött mindenféle készlékkel, akármilyen semmire nem szabadott menni. Úgy felrántott az összes is ellen a falra a békát, a folyosón.
Kérdésem megmondás, amiket a volt szoba szolgálni vágánycsőbe futott, és ezen a plastik ablakkal zárták, és hallottam egyszer életekből rengeteg. Neked körülbelül mint így egy feketét a színvonal lehetett, hogy a csőbe minden a szoba nincs. És ez volt az összerűs, hogy ékesség volt a szobában.
De nekem a szemesben mindig a kedves történet, ami mennyire lesz, ami levágta.
Az is tök jó sztori, amikor elkezdték tesztelni, hogy melyik kábel lesz alkalmas az ellenzékon, hogy ne rágják meg az állatot. És akkor ez a Noémi és a Szilási Zoli, hogy így ilyen rácsárokat lettek, berakták őket a dobozba, és így berakták a kábeleket, és nézték, hogy melyiket szabadítani. És ez egyébként ez a centnek egy kísérlet, vagy egy alkalmazott eredménye, utána az autógyártók átvették ezt, hogy aggódják se a belső kábeleknek. De ott fizikusok megnyerjük. Segélyre is, megnyitök is. Melyik kábelt szeretnél? De ugyanúgy elmondja, amikor az égtetőséget is, az úgynevezett közt, az is a Szilási Zoli. Jöttek a parkolóval, és rakták a kábeleket, és a lángszóróban próbálták megnézni, de így hívnak. Mikor kiválasztották, és megtettek közbeszólás, és ez nekik
nem azt, hogy jóval jönnek tetszik. De jó.
Azt mondom, hogy egyszer eladjuk lévő parkolóba, kidulladt egy autó. Így az volt, hogy hát dolgoztunk ennyivel valamit tettél meg, és és az volt, hogy hívókat bemegyek a parkolóshoz, a parkolóra, de akkor szóval neki csábítunk meg, aminek kell szépen még mondom, így ott ég egy autó. Mit csináltam? Oda mentünk, elkezdtünk velem. Az első tanulság, hogy van ez az autós forradalom, azt felejtettem. Forrott a hav kategória. Nyomtuk rá, és így tök jó volt. Néztünk semmi. Utána rányomtunk kétekről vizet egy slagból, azt se csinálni semmi. Megjöttek a tűzoltók, jött a vizével, megjöttek a megcsalva, hogy felcsomtam vízzel az autót. Öltek egy jegyzőkönyvet, aztán kérdeztem, hogy működtek, és akkor elvállalok a megnézték, és azt volt, hogy így valami 4 méter rágta a kábel, a kábel meg a szikra az oldalt elkapta, az oldalt benzincsövel, és így nem robbant föl, az egy a szarvad, amikor ilyen slagoló követő voltam, és ez az először, amikor egy ilyen lángoló autóhoz így mondjuk olyan, hogy ütöttem a motort, ahol úgy érezhető volt, hogy abban húsz-húsz de semmi nem csinálták. Amikor így látod, hogy elég egy autó izél, az tényleg jó.
Azt ott kell hagyni.
Ott kell hagyni, csip-csip, és így. Ez mi? Ez végre igen, mert ez a dízel. Nem, erről voltak hírek, tehát az egyik sorozatú BMW-nek ez egy gyári hibája, hogy túlpörgeti tehát ugye amikor sokáig mész üresre, akkor az elektronika tudja, hogy most kell katalizátort égetni. És elkezdi égetni a katalizátort, de annyira átkonekszik ettől a motor az intenzív használattól, hogy utána nem kell hozzá egy csak. És hiába veszed le az áramot, nem tudom én, mit nem áll le a motor, és az van, hogy túlpörgeti, utána szépen a hulladás és egy pillanat alatt leégző. És az jobb, több éves.
Jaj, fasz, tudtam, hogy valamit elfelejtettem. Igen, ezt ugye lehet.
A channel az nagyon lassan. A channel az szándékosan el van csúszva. Nem tudom, hány van, de... Tehát az ugyanaz a kérdés, hogy mindenféle.
Nem volna dolog.
És akkor ilyen szó, hogy
Elvileg ez gondolom mégis.
történik, de ki lesz, hogy egy kicsit.
Mi látszik belőlünk?
Az.
Az akkor igazából mire belőlünk? Hol a mikrofon? Az.
Miben beszéljek?
Szerintem ott vagy a mikrofonnál.
Igen, az íznek van egy ilyen közben egy ilyen.
Tessék kiveszni.
És az előadáshoz?
Az.
Azt ott nem nyitni. Azt hittem, hogy beállítottam.
Gyorsan megcsinálom. Csak előgyorsul most az egész.
Szintén kísérletekre van egy.
Ja, ez így olyan, hogy csúnyát mondasz, még levessen. Okay, welcome everyone. We are just in time to start the second day of the Wigner GPU Day. And let me introduce Gábor Bíró, who is a key member of the Wigner GPU Laboratory from a long time. He's one of the key programmer of the Hygiene++ project, which is a very important project in the heavy ion theory group and also in the experimental group. So Gábor will speak about the recent results of the Hygiene++ development, which is a parallel Monte Carlo simulator for high energy physics simulations. So Gábor, as soon as we can set the presentation, please take your place.
So, good morning, welcome everyone. Welcome everyone on the second day of the 10th GPU Day. I'm Gábor Bíró. I'm a doctoral candidate working here at the Wigner Research Center for Physics. And I would like to open this morning session by introducing the high energy Monte Carlo simulations. First, I would like to So first, the question is that what are we doing with high energy heavy ion physics? One of the main objectives of high energy heavy ion physics is to investigate the properties of the quark-gluon plasma. The hot and dense exotic matter existed shortly after the Big Bang, and that we can reproduce at the high energy heavy ion collisions. And I also wanted to show some motivations of the Monte Carlo event generators, but fortunately I don't have to, because Alberto already did it for me yesterday when in his very great lecture he said that modern day high energy physics requires high performance computing relying on Monte Carlo simulations. So you basically already know that my topic is important. So what do we want to simulate with this kind of Monte Carlo event generators? We want to simulate, for example, proton-proton collisions that you can see here. And the problem is that these proton-proton collisions are complicated, as you can see here, because there are a lot of different kind of processes that can happen during these collisions. There are some perturbative QCD processes that we can calculate. There are also some phenomenological processes that has also some empirical parameters that need to be tuned. But the main point is that it doesn't matter what you want to use these simulations. You want to test some new theories, or you want to perform further detector simulations. You will probably want to do these simulations millions or hundreds of millions of times, which will need a lot of computational time. But we also want to do heavy ion simulations, like my title says, which are even much more complicated, because there are not just simple proton-proton collisions, but there are many different nucleon-nucleon interactions. And this will need even much more computational time. And this is still not the end of the story, because it turns out that heavy ion collisions is not just the sum of the different nucleon-nucleon collisions, but we will also have additional nuclear effects like jet quenching or chronin enhancement, which will require even much more computational time. So the main message of this slide is that we will need tons of random numbers. We will need a lot of computational time in order to have the desired precision, and that in Monte Carlo simulations there are empirical parameters. There are some empirical parameters that need to be tuned. So what is tuning? Tuning is basically nothing else, just to set these parameters to fit the experimental data as good as possible. So it is basically nothing, just an iterative chi-square minimization, and everybody knows how to do that, so it's simple. You just have to sample your parameters, run the simulations many times, and do the minimization, and repeat the same procedure until you are satisfied with the result. Okay, that's nice, but if you want to do your minimization, you probably want to use more data points, not just 2. So you have to do your simulations much more time, and you have to do this many times. You will need even more computational resources, but this is even more complicated, because if you want to have a good fit, if you want to have a good Monte Carlo event generator, you want to fit as many experimental results as possible. So you also want to investigate different kind of experimental data, and this leads to a very complex problem, where you can say that Monte Carlo tuning is not just an iterative chi-square minimization anymore, especially if you want to tune several different parameters, where this kind of minimization turns into a very complex, very complex minimization problem in a very multidimensional space. So this is a very serious business, we can say, and we can have different specific tools that are developed to help these kind of tuning processes. And just to give some feeling about the complexity of this task, I want to show a real world example. Maybe some of you know PTIA is one of the widely used Monte Carlo event generators. that is kind of a standard in high energy physics. And this PTR has a standard default tune called Monash, developed several years ago. And the paper of this Monash tune has 57 pages describing more than 30 parameters, the tune of 30 parameters. And this paper has almost 700 citations. So I hope that gives the feeling that Monte Carlo tuning is a very serious business and it's not simple at all. So here you can see a few examples of this real-world tuning and the data sets for what kind of data sets can you tune. Here you can see different collision energies, different distributions of different particles, also the ratio of these particles. And this is just a small selection of the experimental data that you can use for tuning your Monte Carlo. So what I'm going to talk about and introduce you is the Hijing ++ event generator, which stands for Heavy Ion Jet Interaction Generator, inspired by the almost 3,000 years old Chinese book called Yijing, which you can think about that Hijing is the new edition of this book of divination, which can be translated roughly as nuclear change theory. So it is so successful that this first Fortran version, developed almost 30 years ago, is still very widely used in the high energy physics community. But the time has come and there is a strong need for a new modern version of this event generator, which is called Hijing ++ that I'm also developing. And it has many different requirements. So here in this table, I just summarized with bold that the most important new features, most important new technical features of this event generator. And this includes a multi-threading model with which you can use the multiple cores of the CPU. It has an analysis interface, so it is intuitive, it's easy to use. And it has a module management system, like here you can see. So with that, it will be easy to upgrade later with new features. So on the next slide, you can see some of the performance tests of the multi-threaded Hijing ++ with two different architectures. On the upper row, you can see the tests of the test I made with my laptop, which is actually an energy efficient laptop. So it is not a very big surprise that if you see that the speed up that I can achieve with my laptop is not very big. So definitely the laptops are not designed for number crunching. But if you can see on this row, if you use a Hijing ++ with a much more powerful CPU for workstations, you can actually achieve a very good speed up. Next page. So let's return to the Monte Carlo tuning. As I said, tuning is a very computationally demanding process. It's very greedy. You will need a lot of computations. And of course, you won't do that on your own laptop. But like as I did, you will use, for example, the machines of the Wigner data center. And here you can see that if you use many machines with many cores, you can achieve very, very good speed up. And thanks to that, the iteration, one iteration of this tuning, you know that I said that it is an iterative process. You will have to do this many times. But one iteration using the multi-threaded Hijing ++ with high performance computing clusters, I needed only 2-3 days of one iteration instead of weeks, which is a great help, I need much less time for one iteration, which also means that I need much less electricity, and that also means that these kind of computations need much less money. So basically, this is a success. So I arrived to my summary. So I introduced you the Monte Carlo event generators, why are they very important in high energy physics. I showed you that they are very greedy, they need a lot of computational resources, both to operate them and also to develop them. I also introduced you the Hygiene++, which will be the next generation of high energy heavy ion simulations. It has a multi-threaded mode. It is modular, very intuitive, easy to use, and of course, there is still a lot of room for future improvement. We also still need to tune it, which is time-consuming, and later we can improve it with many more interesting features. So thank you for your attention, and let's enjoy the 10th GPU Day.
Okay, thank you very much, Gabor. Let's see if you have questions from outside. We have about 10 people on the Zoom, and I do not know how many on the YouTube. Any question from outside? Inside? Tony.
You have shown the chi-squared surface, which is very complicated. My question is that how crucial is that you find the best minimum at all? So if it is well defined enough, which is the best one?
Very good question. It is absolutely not very well defined, especially if you have more parameters to tune. It is very hard to find the global minimum which will give you the best fit. So that's the reason why it is a very complicated process. And actually, there are some parameters that have very high sensitivity, and some other parameters have less sensitivity. Also, the regions, the observable quantities that you want to simulate, they also depend on which parameter you tune and which range you are investigating. So yes, it's a very difficult task. There are, as I showed, there are some tools that are developed to make this process easier. But actually, I will be very interested in a machine learning-based approach in the near future.
Maybe I can make a remark in addition to this, that the funny thing that you can find very easily a very well optimization for the parameters, but the evil is in the minor parts. So the point is that you have a physical interpretation of some of the parameters, what you use when you build up the model, and you know that what could be the proper values for these parameters. And when you include these parameters, or you would like to get something which is really close to the model estimated a priori value, then it makes much more problem, because then you want to set them to the proper place, because you know that some physics depends on that very well. And then there are still 15 parameters which can be anything, but once you try to force to the local minima in this parameter space, then it's very hard to find normal values for the others. So it's a kind of balancing. So we tried this even with a completely unphysical set of parameters, you can get better result.
Yes.
Okay, which means something. Okay, any further things? Okay, if there's no, let's thank Gabor again.
Thank you.
And let's ask the next speaker, who is István, I think. Yes, István, are you online?
Yes, can you hear me? Hello.
Hey, can you share your slides?
No, we cannot,
because we have the...
Can you hear me?
Yeah. Now we can see you, okay.
And can you also hear me?
Yeah.
Yes, we can hear you.
Okay. So, okay. Here I share my slides. Okay. Can you see the slides?
Yes.
Okay. Sorry. Oh, okay. Hello, everyone, again, and thank you for the opportunity. Here, I will talk about what nanoplasmonic laser fusion research is, and then I will explain our considerations for the target. Then I will compare two open source software which we plan to use in this research, and finally I will conclude which software should we use. And I will emphasize here that this is a new laboratory, the nanoplasmonic laser fusion research laboratory, which has started recently. It is a very large group of researchers, a theoretical group, a laser group, and there are some materials specialists and spectroscopy group. The aim of this research is to study nanoplasmonic effects of gold nanoparticles, which will be implanted inside the target. And of course, the very long-term goal is to help in some way the laser fusion research area. So thermonuclear fusion does not happen spontaneously on Earth. If we know the total energy and the usable energy, of course, and the losses, we can calculate a gain factor, and to have very clean and affordable energy in the future for energy production, we must calculate this gain factor. And we will only achieve if we can fulfill the Larsen criterion. Currently there are two main directions that are researched: the magnetic and inertial confinement. Inertial confinement is where the density of the plasma is increased. There are two main directions of the inertial confinement fusion as well. The first one is a direct drive, which contains the target, and the laser beam hits directly the target, and the biggest experiment is in the National Ignition Facility, Lawrence Livermore, where it is an indirect drive where the laser the laser beams come inside the whole room like this through the two holes on the top and bottom of the whole room. More than 190 laser beams excite the whole room, and X-rays then will indirectly heat up the target, which has an outside layer, an ablator, and in the first step, the target is compressed by that outside layer, and when the second step is the target is ignited and burns. That would be in theory. However, the research and the development is hindered by Rayleigh-Taylor instabilities, partly because the energy cannot be delivered symmetrically as in theory in every point of the target, and we propose the non-platonic laser fusion research project to mainly avoid these instabilities. From heavy ion collisions, we know that space-like surfaces can smoothly change to time-like surfaces due to the points of the shock front in these cases are not connected, not have a causal connectivity. If we heat with constant absorptivity, here is the light cone. We will see that before the light reaches the other part of the target, there is a small time-like front. However, this simultaneous ignition is only enough to heat a small portion of the target. However, if we dope with gold nanoshells, which are resonant at for example, at 800 nanometer wavelength, we can alter the absorptivity to an extent in which we might achieve simultaneous ignition faster. We consider the flat target, which has a minimized surface area. And for example, on one-sided irradiation, for example, we see that without a nanoshell, the deposited energy does not even reach the middle. However, if we alter the absorptivity of the target, the deposited energy reaches much much further. Similar two-sided configuration was already proved successful by this group. They achieved higher compression on lower with lower energy. The nanoplasmonic laser fusion research laboratory is also preparing with experiments. So the aim is to research how the gold nano implants alter the absorptivity of the target. The first target which we can use with the lasers in our institute is a dental monomer with the UDMA, which and the theoretical group, the theoretical group has to provide sufficient information for the experimental group to what setups they could use, and for that we use particle in cell method. There are a lot of peak method software which are available online that are also open source. There are also software which are not open source, however, extending those would be harder. Even open source software is hard to extend, but they at least share the code. We chose the Epoch code is written in Fortran, and the Picanto is written in C++. In general, the particle in cell methods use marker particles, which are inside the cell, and they are driven with a particle pusher and finite difference time domain method, usually used for solving the Maxwell equations. The Epoch code layout is also uses general leapfrog method, in which the half time step the fields are calculated. Then the particle pusher calculates the forces and the momenta using the fields calculated at half time. Then the full time fields are calculated with the resulted currents. The Epoch has an input deck which is very user friendly, and in the housekeeping is usually for the calculation for the computing. There are also physics packages, and I will tell you about that later. So what I already mentioned, the necessary fields are calculated at half time. Then the particle pusher calculates the current, and the particle pusher solves the relativistic equation of motion, this one, and the current deposition scheme which the epoch uses is the Buneman. And then also there is a particle shape, because we know the marker particles are not particles; they are representing many, for example, many electrons, and one important thing is that the momenta is usually calculated so that the shape of the particle is not taken into account. So the momenta is actually one marker particle. However, the fields that are calculated, which then will be applied to the particle, take into account the shape of the particle, for which usually this triangle shape is used, which is the fastest one, meaning that fast but not that precise, but it is more precise than a top hat shape. But in the epoch code, the quadratic spline is also implemented. However, of course, the epoch code does have a few features that we might need. For example, the rough box or grating or grid stretching feature. The grid stretching feature, which can be used, for example, to study Rayleigh-Taylor instabilities, and also the rough box and the grating features can study surface plasmonics. So the publications they published are very promising. The Picante code also has an advanced output strategy. The epoch code uses this kind of strategy where our tasks write into the same file. However, the epoch has an advanced feature that there are a group of tasks who respond to a master task, and multiple master tasks write into a file, which scales very well as the MPI tasks increase. However, the epoch code is, the Picante code is still in beta version and has been for at least 3 years. So the modification that was made, I think, was 2 years ago in the GitHub repository. Yes. So it is not a widely used the software. However, it is very promising. It has very promising features. However, does not contain ionization, which will be very necessary in our case, because short laser pulses will be used with high energies in the scale where in that scale even nonlinear optics has to be taken into account. The epoch software does include multiple ionizations, from multiphoton ionizations to tunneling ionizations, and the epoch code is used also LE Labs. And finally, arriving to the conclusion, the mechanical pressure-driven processes are subject to radiator instabilities. Our research group aims to solve that problem with adjustable absorption of a target. And for more realistic estimates, we need a relativistic analysis. And for the first steps of the research laboratory, we need to provide information and to use a software which is more experimental physicist friendly. So since epoch is used more widely, I think from the two softwares, I would choose the epoch software. But in the next in the next 3 months, I would like to implement at least a few features of the Picante, because I forgot to mention that the epoch is very very extendable, so they thought about that as well. Thank you for your attention. Did you hear me? Can you hear me? Can you hear me?
Yes.
Wait a second. Okay, can you hear us?
Yes.
Okay. So there was a question from Gabor Pap, if he is here. Gabor, please, you can ask your question.
Oh.
Gabor? We can't hear you. So, okay, anyway, so there is a question, István, you may also see. So I could get the point, I couldn't get the point, the transparency show UDMA. What are you using? Yeah, can you see in the chat?
Yes, I see. The UDMA is our first target. It is the target which will be doped with the gold nanoshell. So our first target is not going to be hydrogen, but it will be this UDMA. So it is the whole target, which will have a length of around 20 to 100 micrometers.
Okay. Any question from here? Oh, I would have also a question. You mentioned that the first step will include some, you said on the last slide, that smaller laser with monomer targets. What do you mean on smaller lasers here? So is it ELI, or is it some much more smaller laser like in the laboratory here in the Wigner?
Oh, it is a smaller laser, like smaller than the LE laser, for example, it is much more like the lasers we have in Wigner Institute.
Oh,
So it is 10 to the 70 watts per square centimeter is, I think, the max intensity of that.
Oh, sounds good. So we can do this in a tabletop. We have also a question from Olena Lindley. Olena, are you online?
Yes, hello.
Please.
Yeah, I'm sorry if I missed it in your simulations description. Have you run it on GPUs? Do you plan to? I understood that it's parallelizable, but is it also easy to run on GPUs?
Oh, I'm sorry, I forgot to put it in the slide that these are MPI processes. In a longer term, we might put them on GPUs. The first step is to somehow merge the benefit of the two software.
Thank you.
Okay, thank you very much. So any further?
I still have a question.
Laci, please increase your volume, please.
Okay, I mean, microphone
It's
volume
very
I don't think I have, but let's see. Is it better now?
Not really.
No, okay. I don't know how to change the volume of my mic. I try to speak louder.
Okay.
So my question is that in the epoch code, we do not have compressional energy and equation of state, while in the Picante code, these are existing, and that is what you want to combine. And of course, if you reach higher nuclear densities, then even the ions, which can be protons or deuterium or tritium, are having already some interaction, nuclear interaction among each other. And then you also have electrons where, I mean, of course, the total energy density is less in there. Is the Picante code having both equation of states for the ion gas or ion particles and the electrons, or and even interactions other than electromagnetic interactions between the ions and the electrons? And which do you implement?
There are in the Picante there are a lot of unfinished, not a lot of, but maybe it was me. I found a lot of unfinished functions which have to do comments on them, and the drawback of the Picante code is that it is not very well commented, so not a developer friendly. No, I did not. I could not find what you mentioned. Even so there is no ionization effect, and for the wake field, you have to have separate ion marker particles and electron marker particles.
Mm-hmm. Okay. Yeah, so there is still work to do even compared to Picante, because Picante doesn't include everything. Okay. Yeah, thank you very much.
Yeah. Okay.
Thank you, Laci. Okay, so I cannot see any raised hand or something, so please, first of all, let me thank to István again, and we wish you a successful research for the future. Thank you. And let me ask Balázs Asztalos to join and share the screen and yourself. Balázs,
everyone, just 1 second.
Balázs is a nice example. He is also part of the GPU laboratory. As you know that you can be a staff member only if you are Balázs.
Well, hi everyone.
Okay, please.
You can see me, and do you see the presentation as well?
Yes.
Perfect. Okay, so hi everyone. My name is Balázs Asztos, and I am actually now a PhD student with Gergely in the GPU laboratory and in Alta. Just started this September. The presentation I will share with you is based on the work that I did as part of my master thesis, and it's about astronomy, and it's about how GPU can be.
Balázs, sorry, your voice is a bit weak. Can you make it?
Let me try to bring this a bit closer. Can you hear me better now?
Something like.
Is it any better or not really?
Okay, let's try this way.
Yeah, let me. I mean, I'm pretty close to the microphone. But tell me if it's wrong, then I will try to get a headset connected. Can you hear me?
Yeah, seems okay. Better.
Okay, yeah. So this work kind of speaks about astronomy mostly, but it shows how GPU can be leveraged even on a beginner level, because I would not position myself as a GPU expert, but rather someone who is doing modeling and wants to borrow some techniques, including GPU, to enhance the way I can do my modeling work. So many of the things that I will mention probably will be relatively familiar or even basics to you. But I think one very important message that I would like to send, and not necessarily to you, but to the broader community, is that GPUs are there. We should use it much more often, even in the everyday modeling work. And to make that possible, I think we need to do a few steps about making it easier to use on the entry beginner level. Now, let me speak about the physics and the astronomy a little bit behind this work. So I was working on modeling typical normal stars and wanted to see how their inner structure is changing when they are not alone anymore, but there is a close binary or close accompanying star. So on this opening image, you can see a kind of graphics. I mean, it's an artificial graphics, but it shows that clearly gravity influences how the star surface is formed or deformed, and this, of course, has impact on the inner structure as well. So why is this important? Clearly, we know a lot about stars. We have been modeling them for a long time, but it has been just in the recent years that we started to kind of understand more and more of very close binary stars and solar systems similar to the solar system, or not very similar because of much larger accompanying objects in those. Some of these new observations were obtained through the Kepler Space Telescope, which was originally kind of sent up to collect information on planets orbiting stars, but in a later phase, it was collecting a lot of data on binaries as well. Also, I'm pretty sure all of you know about the recent discoveries by the gravitational wave detectors about merging black holes or merging neutron stars. And clearly this also brings us closer to the question of what happens when stars are very close, they are deforming each other, and they are potentially not only deforming each other, but the orbitational properties or mechanics as well. This many new data that we are receiving, of course, makes only sense if we understand what's inside these stars and how these stars evolve, and that modeling has to happen through various kind of tools, setting up new models, and I'm going to demonstrate one of these models. To be honest, GPU was not the primary purpose of this exercise, but rather a tool leveraged in it, and the learnings pretty much show towards kind of the necessity or the advantage of using GPUs in follow-up studies. In this presentation, I will quickly talk about the physics of this star model that I built up, which is the polytropic star model. Also, the external gravity field of the other star, the fixed rotation, and the centrifugal force resulting from that. Then I will briefly talk about the validation of this model that I built up, and also some first results that show how the deformation happened. The model was first implemented in Python to verify that it actually works, and then C version, and then I ported it to GPU platform for speed increase. The star model, I mean, I don't want to go very deep into the physics, but practically probably all you can imagine that if there are no external gravity fields, then it's, and if let's assume the simplest case when there is no rotation, nothing, then you can kind of define this as a very symmetrical model that pretty much the pressure and the gravity is kind of in balance at every point in the star. Now, if you start applying centrifugal force, the rotation of the star, or potentially two or multiple stars rotating around each other, then you can kind of imagine that, yes, for each point in the star, there will still be an equilibrium of the forces, but they will be the resulting kind of equilibrium will be at a different point compared to the completely symmetrical case. So these are the effects or forces that are included, and that's included in the top equation. Now, the other element of the model is that for each of these star models, you need to have some kind of relationship between the mass, the pressure of the and the density of the material in the star, and that's described by this polytropic star model in this case, which is based on the equation P equal K times rho up to the gamma, where gamma can take various numbers. This is one model. There could be many other models. The developed model can actually kind of work very well with other models because it's based on incremental building of the star, each layer by layer evaluating the equilibrium based on the equation number 3. I don't want to go deep into the polytropic star model, but rather come back to this kind of description of the model and highlight that when I say that for each element or each position in the star, depending on how kind of high or low resolution you choose, you have to evaluate these equilibrium conditions for the forces. And this is where right away you as GPU experts would be able to say that, yes, this model is highly prone for parallelization, so that GPU could be kind of leveraged to do these calculations in a parallel manner. And that's that was the kind of inspiration later on to bring in GPU processing. So let me speak a little bit about the GPU model. So this was a relatively simple model, as the key question here was how to make these calculations more efficient, faster, and at the same time doing this in a relatively simple manner. So practically the code itself, why it was first developed in a Python code for verification. The porting happened in a way that the code was separated into two big chunks, or I mean, into many smaller pieces. And for each piece, there was a decision whether this should still stay on the CPU or go onto the GPU. And probably it's not very surprising that the key pieces that went to the GPU were the ones where the multiple threads could run parallel or relatively in a parallel manner with some synchronization. Highly repetitive tasks like root finding algorithm and the calculation of the external gravity and centrifugal force. These were the key pieces implemented on GPU because these were not only run in a very high number, the same functions, but these could be run in a parallel manner. The CPU kept the more and whether high level task or more the organizing tasks like setting up the simulation, installing the CUDA environment, allocating and managing the storage, and sequencing the tasks that were performed by the GPU. Let me show you some results. I mean, this could be more interesting for astronomers, but the important element of this model was that for certain parameters, this could actually bring back the features of known objects. So one of this is our own sun. The polytropic model actually is a relatively good description of the sun that we have, and with pressure and densities defined in the center that of our sun, I managed to actually get a very good kind of match with the other results from other research. Another verification is that there are this polytropic model has a few analytic solutions for very specific numbers, and those solutions were also tested. Another interesting kind of way to verify or test a model like this is to use the Roche radius calculation. In astronomy, this is the effect of gravity on a body, and around the body there is actually a limit where that body's gravity is more strong than the other body. So when you look at this figure, if I mean the other body is not shown, but it's on the left side, whatever is inside these curves, those will be more attracted to the center of this body, while the anything outside of this limit or Roche radius, those objects would be pulled more strongly to the other body. So this is something that can be analytically defined and calculated. And my star model, of course, is not using this kind of analytic calculation, but can be verified against this. Okay, a few verifications. So, for example, on the left side, you see the Roche or Roche radius with red, and the resulting star with the green dots. Clearly, they are not exactly the same, and this comes partially from the other rotation. So this model, the Roche model, is for two stars and not necessarily taking into account its own rotation of the star. This figure shows the density and the pressure distribution in the star. What you can see that on the tip, which is closer to the other star, there is significant difference to other parts of the star or other surface regions of the star, but the inner parts of the star is much less impacted than you would think. Similar results were obtained with various star masses and radius between the accompanying stars. And clearly, when you were kind of using models where the accompanying star is closer, then you get significantly larger shape distortion. With 4 or 5 sound radius, the distortion becomes much smaller. On the lower figures can show this more clearly than the ovals on the top. Similar results are also found when the star size or star mass is increased with a fixed radius. Of course, larger masses will bring larger distortion, but as you can see, the type of or the shape of the distortion is different when you use when you are increasing the size of the accompanying star versus when you were increasing the radius. If you look at this figure on the top right hand side or top left hand side, you see that the deformation has a different shape. Okay, a few thoughts about the CUDA or the GPU implementation. And that's where I'm clearly a beginner in this field, but I also found that why not too many beginners are joining, or at least trying out, or maybe they are trying out, but they might not even be able to get across the first hurdles. Setting up the environment, I chose a Microsoft Visual C++ environment. It wasn't straightforward at all. So there were various settings that needed Stack Overflow help and other expert helps, or at least asking experts, like the execution time limit on Windows, which of course makes sense for any graphic application where the screen refresh is an important feature, but for a physics calculation, this 2-second limit that I actually had to overcome by programming and was unfortunately not able to change it. That makes, of course, physics a bit more limited. The advantage of the GPU, I found that it can only be really kind of captured if the tasks are carefully separated between CPU and GPU. Memory copy, as it's advised at many places in literature, has to be really limited, otherwise all the time gain disappears there. And the number of threads actually, of course, GPU on a single thread is more slower than the CPU. So what I found that at least 20 threads were needed in this case to actually achieve equal speed to just a CPU implementation. However, with higher resolution, this was very fast, or at least linearly fast, increasing the speed. And that actually has a very important feature that this enables researchers to kind of test much higher resolution in their modeling compared to a smaller resolution where the CPU probably actually wins over a GPU. In my case, when it was a spherical modeling and in the second phase it wasn't symmetrical anymore when rotation and centrifugal force and the accompanying star was assumed, then this feature of the GPU being able to evaluate parallel in many threads can help a lot increase the resolution. in summary, I don't want to repeat this again. What I just want to say is that in my continued research, which I'm focusing on neutron stars, I'm planning to further GPU implementation, so I might be able to bring back some more interesting results in one of the next conferences. Thanks a lot for your attention, and let me know if you have any questions, comments, suggestions.
No. Okay, thank you, Balázs. I'm looking if there is. Yeah, there is one question.
I wrote it.
Yeah, okay, so please. Just in front of you.
Hello, my question is that do you use the PGI compiler, Fortran or C compiler with CUDA support?
I couldn't really hear the question, but about the compiler. So I was using the Microsoft Visual environment to compile the code.
Yes, this is just a comment that since NVIDIA bought the PGI and they support the compiler development, the PGI compiler is a really good one for Fortran or C development with CUDA support. So and now it is free of charge.
Okay.
So yearly 2 versions of it are free.
Thanks a lot for the suggestions. I will definitely have, look for it and check it out.
Okay, further questions, Tony?
It's maybe a naive question that you showed the Roche surface, and this for me it looks like a tidal wave, the one part of the tidal wave. I mean, there are the other part, and because of rotation. How enhanced and how important in the rotating binary is this other tidal wave?
You mean tidal wave?
Yeah. So there is a bump on one side here, but because in the Earth there is another one.
Yeah. So okay. So for most binaries, they are so close to each other that eventually these objects, and whether it's stars or whether we look at the Earth-Moon system, they are logged actually to each other. And therefore there is actually no tidal wave, but they are pretty much pointing towards each other when they are rotating.
Balázs, I had an idea during the talk that is there any sensitivity on the sign of the equation of state in this calculation? So, for example, if you would change the k in the equation of state to negative values, does it matter in the calculation?
I mean, the polytrope model usually, and I had a slide, I didn't go too deep into that. In the polytrope model, you usually use a positive number. So you see the gamma, where gamma is 1 plus 1 over n, and n, if you go back to the equation of state, p times volume up to the n equal constant. So that's the polytrope model. So in that sense, gamma cannot go into that.
Not the gamma, the constant parameter. I mean, maybe just try. So if I can ask you to make a run with negative k, I would be interested in if the code can survive or not.
Okay, this k. Okay, to be honest, I have not tested it, but we could look for it and see what it. I mean, the model is there. We can change the k and see what happens.
Yeah. Okay. Any further questions? I cannot see neither from inside nor outside. So, okay, let's thank Balázs again. And now we are making a quick 10 minutes break, and then we continue with another astronomy talk with Kundan Tadam from the Konkoy Observatory. So stay tuned, and we are back in 10 minutes. Thank you.
Thank you very much.
Okay. We are back. Can you hear me? Kuman? Hi?
Yes, I can hear you.
Oh, can you increase the volume a bit?
Yeah, sure, but I think the problem might be on your side in the sense.
Oh yeah, let me see.
Just increase the speaker volume, so. And I'll start sharing the screen.
But the point is, some of the speakers has a very good sound and good quality. But okay, so we can hear you at a certain point.
Okay.
Okay, so welcome back, everybody. So the last session of the GPU day, and Kundan Kadam from the Konkoly Observatory, and he will speak about the hydrodynamic modeling of protoplanetary disk with G-Fargo2. So please.
Yes. You can see my slides?
Yeah.
Okay, great. So yeah, first of all, thanks to the organizers for giving me this opportunity to talk. So I'm Kundan Kadam. I'm a postdoc at Konkoly Observatory. So I work with Agnieszka Koshpal's ERC group, and today I'll be talking to you about hydrodynamic modeling of protoplanetary disks with a GPU-based code. So this is the structure of the talk. I'll be talking about astrophysical context, hydrodynamic modeling that we do, some new results that we have, and advantages of GPUs in these calculations. So I'm not really an expert in GPUs, but hopefully this talk will be at least entertaining for you guys. So the astrophysical context in this case is planet formation in protoplanetary disks. So the story of planet formation goes from large scale to small scale. So you have this large scale structure on cosmological scale. You have the gravitational collapse into galaxies. Each galaxy contains about 100 billion stars. And the galaxy also has these giant molecular clouds, which are basically the nurseries for star formation. And inside these clouds, you have protoplanetary disks. So these are rotationally supported because of the conservation of angular momentum. So this goes from cosmological scales to about 100 or thousands of AUs. And the story of planet formation is also a story from going from small scales to larger scales. So you have interstellar dust, which is produced by processes like supernova and so on. And we think that planets are produced via this dust. And in the protoplanetary disk, this dust grows to larger and larger sizes. So millimeter size, it's something like poppy seeds, which you can see. Then meter size, and then kilometer sized planetesimals. And once you have planetesimals, gravity can take over, to form planets. So going from dust scale to planets, it's about 13th order of magnitude increase in size, and about 39 orders of magnitude increase in mass. So it spans a large amount of a large span of physics, basically. And in general, what happens is that you have initially a gas-rich protoplanetary disk, and some processes you have growth of dust, and you have planets, planetesimals, and at the end you have planetary systems when the n-body dynamics dominate the interactions. And I forgot to mention one thing on the previous slide is that this jump from about meter size to kilometer size objects that I showed here, it's not easy to model because there are several barriers in the way, which I'll talk about in upcoming slides. So observationally, with different techniques, you can probe different regions of a protoplanetary disk. So if you use near infrared wavelengths, you basically see the scattered light of the central star. So these are the gas content. So you just see the surface in yellow. If you use sub-millimeter wavelength, like the large radio antennas, you see the solid content. So that's the midplane. And these are some of the images that you might expect. So on the left-hand side, you can see that it's not 2D structure. It's basically a flaring structure with some 3D geometry. So that's the infrared image on the left, and on the right-hand side, you have a radio image. So this is the famous HL tau object, in which these rings are observed, and it's thought that these rings may be evidence of planet formation. So the planets carve these gaps. So that's one of the theories to explain this phenomenon. And when we do direct observations of planets, we don't see planets forming, because that phase lasts for a short time. It's also embedded within the parent molecular cloud. So what we see is fully formed systems, all like our solar system. And to go from protoplanetary disks to planets, we have to use models to see what's going on. So on the right-hand side, you have a picture of recently discovered planetary system TRAPPIST-1, which had 7 planets in a single system between about distances of radius of Mars in our solar system. So we use hydrodynamic models to probe these early phases of planet formation. So the model needs to have a gaseous component, because most of the mass is in the gas, and a small amount of solids are present in the form of the dust. But dust evolution is important because the planets are formed out of dust, and it also dominates the opacity, and hence the thermal evolution of the system. And you also have partial ionized material. So magnetohydrodynamic effect also become important. And at some point, radiation effects also become important. So these are the equations that we solve for the gaseous components. So first you have the continuity equation, conservation of mass, basically. Then you have momentum conservation. So on the right-hand side, you have the pressure term, you have viscosity, you have gravitational potential, and you have the drag. So that's the back reaction of the dust. So that's the F drag component. Then you need to solve the energy equation. If it's not an isothermal system, then you have a work term on the right-hand side, and then you have heating and cooling term. So what we use is we just use simple beta cooling technique. Then you have initial and boundary conditions for all of these. And for dust evolution, you have similar continuity equation. And momentum conservation of dust, you don't have the pressure term, because it's a pressureless fluid. Dust is more or less. And the drag term on the right-hand side is same as the drag term that acts on the gas. Then the equation of state we use is basically just adiabatic or ideal gas equation. And then we need to solve for the gravity of all this. And that's very expensive, basically, because it scales as n square interactions. So for gravity, you have central potential of the star, you have self-gravity of the disk, and also something called independent potential, or indirect potential, which is the movement of the star around the barycenter of the star and disk system. So when you try to model, we try to model this using a code called gfargo2. So this is a GPU-based code, but it's originally based on the Fargo code developed by Benitez Lambai and Massey in about year 2000. So there are several versions of the code right now. What they use is, latest one is gfargo 3D, which can model several interactions in 3 dimensions. And there's also a version gfargo, which is GPU based, but what we use is a gfargo 2, which has some additional modules and which is mainly developed by Zsolt Rogalli at the Conklin Observatory. So it's basically in C++ and CUDA implementation, and it's called Fargo because it stands for fast advection in rotating gaseous objects. So that's a type of algorithm in which the equations of transport are solved in the local Keplerian frame of reference. So as a result, what you have is you have improved efficiency because that reduces the constraint on the Courant condition. You also have improved accuracy. And this code basically conserves mass and angular momentum to machine precision. And it's since the geometry of the system, you can imagine it's easier to solve in cylindrical coordinate system. So equally spaced in phi direction and logarithmic spaced in radial direction. And the code also has an n-body integrator if you want to add planets or planetesimal interactions. But we don't work with n-body in this particular case. So previously I mentioned there were some barriers to dust growth. So let's see what they are. So what happens is as the dust collects and grows, it in a gaseous disk, it basically feels a headwind inside the gas. And what ends up happening is that the dust always drifts towards the gas pressure maximum. And as you can imagine, if you're driving in air without an engine, your car will slowly slow down and stop. So basically that's what happens with these dust particles, is that they drift towards the star because they lose angular momentum to the gas. So this is basically a barrier to the growth for the dust particles. You also have something called fragmentation barrier, in which it's related to the relative velocity between dust particles. So if you have two particles approaching each other at, let's say, 10 meters per second, instead of sticking to each other, they end up destroying each other. So that's also a barrier to the growth of the dust. That limits the growth from about a few millimeter size to about a kilometer size particles. So that's very difficult to achieve. So there are also theories like lucky few particles, in which they assume that there are some lucky particles which survive and they end up becoming planetesimals and ultimately planets. So yeah, these are the barriers that I talked about between about meter sized to kilometer sized. And now I'd like to talk to you about some results that we have using these techniques. So one thing I didn't talk to you about is the magnetic connection, so in order to transport mass from the disk to the star, you need to transport angular momentum outwards, and we think that it's done by some kind of turbulent viscosity. So on the right-hand side, you can see an example. So you have water and you have honey or some viscous material. So viscosity is basically this kind of behavior of the material. So in a typical disk, you use what we call a Shakura-Sunyaev prescription. So viscosity, which is nu, is proportional to some local properties of the disk. So you have sound speed and Keplerian velocity on the right-hand side, and alpha is just basically a parameter, which is constant. But in our model, we make a key assumption, is that the dust particles which are in the disk, they absorb the electrons and ions, and they reduce something called MRI viscosity. So I can't go into too much details, but it's related to the coupling between, weak coupling between the charges and the magnetic field. So you have less coupling, you have less viscosity, and your disk behaves like water instead of, let's say, honey. And it transports less angular momentum. So this is one of the key equations. So alpha is not constant in this case. It depends on the dust surface density, sigma d, and gas surface density. And these are the indices that we use. And these values are chosen so that the alpha is essentially proportional to the enhancement in dust. So it's basically proportional to dust to gas ratio. So as a consequence of this is what happens is that if you have slight perturbation in the dust, it enforces a positive feedback loop, so that increase in dust reduces viscosity. So low viscosity accumulates gas, and dust always drifts towards the gas pressure maximum. And you accumulate more dust, which reduces viscosity further. And in one dimension, or in perturbation analysis, linear perturbation analysis, what you have is a single perturbation causes these concentric rings to form. But what we did is we analyzed this model in 2 dimensions. And I'd like to show you this movie. So this is part of a ring. And in 2D, when you let it evolve in our GFargo code, you have these. So basically, the ring becomes Rossby unstable in nonlinear regime, and several vortices form. So this is what you see. And each of these vortices have a pressure maxima at the center, and that's where the dust accumulates really fast. on dynamical timescales. So yeah, this shows an individual vortex. So in this movie, you see what happens after hundreds of orbits. So you have several mature vortices rotating. So some are rotating in one and some are rotating in other direction, because the frame of reference is, well, Keplerian centered at this point, So a key thing is that we don't have just a single, what do you call it? A single ring of vortices at the location of perturbation, but what happens is these vortices generate these spiral waves inside and outside, and constructive interference of the spiral wave generates new generation of vortices. So they basically create a large number of vortices in the disk. And this is a paper we are about to submit to a journal. It's not submitted yet, hopefully this week though. But it shows one of the images in the paper. So on the left-hand side, you have rings in 1D, but in 2D, they become Rossby unstable and create these vortices. And you can also see the velocity structure of these things. And well, since you're not familiar with this code or this method, usually in this code, what you see is structures like this, in which they're studying a single planet in the disk. And in the bottom, you have Rossby instability, but the vortices typically merge without this assumption that the dust particles absorb the ions. So the one, what do you call it, the dusty vortices that you see here, it's a new phenomenon, basically. And why are these results so important? So we basically have a simple physical model in which we make a simple assumptions that dust reduces viscosity by absorbing ions, and we get these large number of vortices. These are stable for thousands of orbits, so these are secularly stable, where dust can accumulate, and it overcomes the drift barrier because these vortices stay in the disk, so the dust particle don't go out of the disk to the inner boundary, basically. And it overcomes the fragmentation barrier because the vortices collect a large amount of dust, so that dust to gas ratio is of the order of unity, and several other instabilities can set in, like streaming instability, to overcome the fragmentation barrier. They collect of the order of 0.1 to 10 Earth masses of dust, which is really good for planetesimal formation. And this is the first model to produce a large number of vortices in a regular disk, in which we don't have to tweak parameters like lower the viscosity a lot, things like that. And what is the role of GPU in all of this? As I showed you in the equations, we have several partial differential equations to solve. So there are two for the velocity component of the gas, one for the gas density, same thing for the dust. But the most expensive part is the gravity. So each point needs to know what each other point is doing, and they're solved in the Fourier space, but still the algorithm scales as n squared, and it's highly parallelizable problem. So these are basically run on clusters of the 3D NAL group at Conkley Observatory. So that stands for Numerical Astrophysical Lab Group. So Joel Trogali, who's my colleague, he's the leader of that group. So he has some clusters in the basement with some Tesla K80s. So it takes about 12 hours to run a simulation with a resolution of 1024 by 512. And one big advantage is that these are energy efficient and also time efficient. So I'm working on other projects which use OpenMP parallelization, and I had to run those simulations for weeks or months. So that's a big advantage with respect to GPUs. We have tested these, similar simulations on Tesla, 2075 cores, which are, I think, older generation. The code runs about 2 times slower. And on Volta 100, it runs about 2 times faster. And in fact, Joel Tregali, he recently won a grant, so he'll get 4 Volta 100s. He'll purchase that soon, basically, with that grant. And I think GPUs are basically future of computational astrophysics, because these problems that we see here are highly parallelizable. So I'll leave you with this slide. So this is Laplace. He lived in 18th century, and at that time he didn't have tools to investigate the planet formation and so on. But he said that sun and planets come together and came together and condensed at the same time out of rotating cloud of gas and dust. So at that time he didn't have tools, but perhaps now with GPU-based tools we can make his idea come alive and investigate what's going on with the solar system. So with that, I can take any questions if you have. Thank you.
I'm asking the online participants first if there would be any questions. No, I cannot see. Anybody from inside? I might have a question if nobody else, which related to your video in the middle of the talk. So what was the time scale of this? Maybe I missed the point.
Okay, so the orbit is calculated at, so this is 1 AU, this point is at. Mm-hmm. So orbit is normalized with respect to the time at 1 AU, and so the ring instability occurs at in about 20 orbits, and after that the vortices become unstable, and that lasts for thousands of orbits. So you can interpret that in terms of years. So they appear within 20 years and last for thousands of years.
And how about the formation of this retrograde like movement when at the final state you had?
That's a good question. So what ends up happening is that these vortices you see, they don't stay in those orbits. They slowly decay because of the spiral waves, they lose angular momentum. So in 1,000 orbits, they'll slowly exit through the inner boundary. But the idea is that they create sufficient conditions for producing large bodies, and they will decouple from the gas, and they will continue maintaining the same trajectory. So.
Oh, this I find pretty good. Okay, one more question in relation to this one. So can you really observe this by Herschel or some other real observation? I mean, in a few years or some decades, can you really measure? Okay, maybe not at this level, but on a similar level, in order to get the proper initial condition for your calculation?
So yeah, that's also a good question. So. So we think that their physical conditions are obviously like condensation fronts, or what do you call it? When the gas freezes into ice and so on, that's where these density jumps can occur, and which is the physical motivation. So here we just perturb the disk with artificial delta function, and that's when we got the rings. But in real disk, you'll have like snow lines and so on for water CO, which can give rise to vortices. But in terms of observations, we don't know what a good test is, because these are distances of the order of 1 AU, which are really hard to probe with even state-of-the-art instruments. So with some instruments, you can see that there's some asymmetry, but to probe something on this small scale, it's not yet possible, I think.
Okay, thank you very much.
Okay, you're welcome.
So, I think there's no further questions. So let me ask Olena to come to the stage. Hi, Olena.
Hello.
We can see you clearly, so you can start.
Can you hear me? Can you hear me okay?
Perfectly.
Okay, great. Then I'll try to share.
So the talk is comparison of very deep learning performance in GPU and CPU, and Olivia is from FIAS Frankfurt University. Please.
Yeah. I'm trying to start, but it's so slow. Wait a second, I don't know why it's not starting to. Yeah, okay. Do you see it now full screen?
Yes, perfect.
Okay, thank you. Thank you. Thank you so much. I'm happy to speak for you, and I really wish that it was in real life and not virtually, and really hope that it will be back to normal at some moment. But better so than not at all. And I'm really enjoying this conference so far. Yesterday we heard a very interesting definition of understanding as classification. And that, of course, explains why the deep learning community spent first valuable years classifying cats and dogs. And I have for you on the right-hand side a picture of an animal, which can be a cat or maybe a dog or maybe something else. And if you would like, remind me, and in the end of the talk, I will tell you what it is, in fact. For me personally, it was very difficult here to decide what type of animal it is. And of course, on a serious note, we have to apply this for something which makes our world better, not just understanding cats and dogs. Some examples are, for example, in medicine, which is now very relevant, or in physics to suppress the background in experiments, or in applications related to social sciences. We want to, for example, control the sentiment of texts for various reasons, for example, removing the bias from texts, or in chatbots to understand what is this text about. So the applications for the classification algorithms are very many possible applications. And I written in the title, very deep learning. So the purpose of this talk is I want to explain what is meant by very deep learning, what are restrictions, and how the GPUs can help us here. People who know me a little bit, they know that I don't like very deep learning. I actually always tried to make a propaganda for less parameters and less layers and make it as simple as possible for the use case in mind. But there are also some cases where you need to go deeper. And for some example classification tasks, we can use machine learning methods starting from decision trees and so-called traditional machine learning up to the more modern deep learning. And for example, here on some real life data set where we had to classify texts which were labeled, it's a supervised task. And there we could clearly see that all the so-called traditional methods, also including the dense neural nets, were not performing as good as a convolutional neural network. It's not a big news, which we now found. It was just a test in our data that indeed all other methods couldn't crack the 94% accuracy in best case, and that was probably already in overfit, while the convolutional neural nets easily gives 98% without overfit. And that was for the first time found in 2012 already, when Krzyzewski and collaborators have won the competition for the classification of images, and for the first time introduced the convolutional neural networks and have proven that this method performed better than any traditional method, including the very, very popular method of engineering, where we first find some labels by engineering input data, analyze our data for per hand, and then try to learn on the predefined labels. And so the deep learning was proven for the first time to work better than traditional methods in 2012 was a classification task, and it was a convolutional network. On the right-hand side is a short mention what convolutional networks are, but I think people in this audience know it, and if not, you can later ask. So the idea in 2014, pretty soon after that came, why don't we go deeper? Means why don't we make the networks bigger? Because then maybe we can fit the unknown function which describes our images better. As we heard yesterday in this book by Tony, is sometimes we just need more dimensions in order to define our class. And if we want to fit more dimensions, then of course we need to go deeper and have more parameters. So that is logical, and it's called the power of depth or the benefit of the depth. But there is a problem, that there are two problems. First is very obvious that if we have more parameters, we are easily falling into the overfit. But that was solved already in 2014, as I said, very soon after introduction of convolutional networks in principle, by Simonian and Gruppe. They introduced so-called very deep convolutional networks architecture, which managed to learn, for example, 54 layers without falling into the overfit. And that is, of course, already a great achievement. There was a problem that with 46 layers, the accuracy was less good than, for example, with 20 layers. So that you can see on the left plot. The important message is that the red curve is above yellow or brown, or whatever color curve. So that shows that although, of course, with iterations, we learn and get better, the network which is bigger and has more freedom to learn actually performs worse than the network which is smaller and simpler. So 56 layers, a lot of expensive computations didn't lead to a better accuracy. Moreover, it seems to saturate. So I cannot get better no matter how long I learn. So that is the second problem, and that is called in the AI communities the vanishing gradients problem, which means that basically you can understand it like that, that when you have many, many layers, by the back propagation, you need to transform the information in the end. Is my prediction correct? You have to transform it backwards in order to change the parameters in the very beginning. And when you have many layers, the information is lost by the time you got back. So the gradients vanished. And that problem for some time was very big and seemed to be unsolvable. In other understanding for the same problem, I would say you can think of it as a very multidimensional optimization problem, because when you have many layers, you have many parameters to fit. And then you have a hypersurface in an extremely multidimensional space. When you try to reach the global minimum in so many dimensions, necessarily your jumps will be too large and you will be trapped always in some other local minimum without possibility to reach the global one. And less layers, less parameters, less minima, less problems. So that fits until now with my philosophy, and I would say then forget about the very deep learning. 20 layers is already good enough until came the ResNet, and this is now the state of the art. So it was introduced in 2015 at the end of the year, and actually the modern version 2016, but I would say until now there was nothing better made. So the ResNet is the best architecture by accuracy for the understanding of images. Understanding of images is a standard task. Is when you see an image, you have to say a name for it, like picture of a woman, picture of a cat, is a painting of Rembrandt. Labels can be variously defined, but the idea is that it's a classification task for images. And you see that the solution, this ResNet, in the paper, the plot shows the right-hand side. Very important message that the red curve for ResNet, that's the very right plot, lies under the blue curve. So for the traditional convolutional network, 34 layers are not better than 18. Within error bars, I would say they're also not worse. So they did their best, but they're also not better. And on the right-hand side, you see that the problem, the conceptual problem of vanishing gradients was solved because the 34 layers give a better performance than 18. At least I would say within 2 sigma. So, so this ResNet, what is it doing? How they managed? So first I show you on the left side one very, very simplified diagram of this architecture, which means on the left side is showing the traditional network, one part of it. So say like I arrive at this layer where I come in with an X. X doesn't have to be my input. It can be also output of a previous layer. And my layer transforms X into f of X. And then I go further. And the ResNet, this is called a block. It can be also 3 layers, usually not more than 3. It's a small normal convolutional network. And on the right-hand side of the scheme, there is a ResNet scheme. It was, by the way, in 2015-16, published by He and collaborators from Microsoft. So it has a so-called shortcut, which is shown here by this line around. And the meaning of the shortcut is the following. The output of this block is not the usual f of x, but it's f of x plus x. What is x? The x was, as I said, either input or the output of the previous block. And f of x is the usual transformation of this x. So why does it help us at all? So the idea is that if you make an output of this block f of x plus x, it means that the x was not fitted. The x was already the input. And that means that what you have is a sum of changed parameters and not changed parameters. And I had to spend some time to understand it, and that's why I'm happy that I can do it for you now and a little bit explain. It is like I tried to fit a complicated function with a lot of wiggles. And instead of trying to find a very large polynomial of very many degrees, in order to explain every possible wiggle, first I make an approximation with a relatively smooth function, which you can see on the right-hand side as an example. So I have a model with less parameters. It's just a short network. It is a very small block. And this block makes for me necessarily not a very detailed approximation, but a relatively smooth one. And then I look at the difference between this approximation and the actual function, which is f of x minus x. And this difference, the residue, which is plotted down, I now fit again with the next block, which I hang on top of this block. And the next block, again, is not a 54 layers, but it's only 3 layers. So it cannot make a very wiggly representation of this residue. It makes a necessarily a smooth representation. So I have a second smooth representation, which I add to the old one in order to make now approximation to the full function. And as I see, this one will also have a residue, and then making another block and another block, hopefully at some moment, I will have several functions, and the sum of them will give me the full function. This way, I can describe very detailed structures without having to fit simultaneously millions of parameters. But instead, I feed something like 1,000, 1,000, 1,000, 1,000, or 100, 100, 100. So it depends on the use case. And this helps to approach the global minimum consequently, also iteratively, without a danger of always jumping in and here, there, back, there, back, there, back. And this is the philosophical now explanation of the ResNet, which is, of course, you can find online the code and the schemes, but I find it very useful to think about what is actually happening. So then the people from Facebook, of course, ask themselves, is it making sense to apply this architecture also beyond the image recognition, also, for example, for the text analysis, because it's also a big question always with artificial intelligence, deep learning. Do we generalize from one use case to the other? Is it possible? And that's also what I do for a living. I generalize from physics to text analysis and back. I find until now it works well. So they also found it in Facebook. And we also in the company analyze texts. For example, we always try to do something useful for our clients. So we can try to use the architecture of convolutional networks, and in particular ResNet, for predicting the click rates based on the title of the website. And this is in German, but the idea is that you can say the same thing in many ways. And we can, instead of experimenting, which is expensive, we can already by simulation predict which way is optimal. And then when our clients started using it, indeed we see that they have a better traffic on the website. So another application, classification of text, means we can also look at the emotional color of this text, sentiment. So in a very simple case, it will say if the person is angry or if it's a happy person, which is writing this text, is the message which is hate or love. Or in this case, we looked if it's a message which is discriminating, or is it gender neutral and anti-biased. And that also helps our clients to be gender neutral, for example. And so where are the GPUs coming? So these use cases, which I just described, is about the websites, in particular career websites of the companies. For the web application, it is enough if the reaction time is below 1 second. And usually people take it, they find it okay, this reaction time. And so our task is always to lie below, let's say, half a second for our analysis, and then it's good enough. So I would say that in this case, our Python code to TensorFlow, even on CPUs, was performing fast enough. But now let's go to a use case where performance is very important. So where 1 second for one decision, or half a second per decision, is just very, very low, very large. So we are talking about now high energy physics experiment at CERN. In this particular collaboration is called NA61 Shine collaboration, where I participate. The event rate is of the order of 100 hertz. And in each event, we produce thousands of particles, and each particle leaves a track consisting of at least order of magnitude 10 hits. So the idea is that we have to analyze signal to background classification so fast that the decision can be done online in real time. Of course, it is impossible with one GPU, one CPU. We have a farm consisting of hundreds of nodes, but the limit is that we have to analyze a whole event, so all particles simultaneously, all tracks and all hits, within maximum 3 seconds per node, if all nodes are fully working. So, and we don't want that also because we need a buffer. So that is a hard limit, 3 seconds. And so the question was, can we reach very good accuracy for which we need a ResNet, a deep network, within only 3 seconds. And of course, we considered not only CPU clusters, but also GPU clusters for that. So the input data in this case is not images of cats, is not words of websites. It's, in this case, it's a readout from electronics in the so-called TPC, which is the main part of this detector. We have 4 bigger TPCs and some small. So which have more than 120,000 pads, and each pad records 200 something time slices. And so the input is such a two-dimensional readout pattern where we have timestamps and pad numbers. So we look simultaneously at 11 neighboring pads and simultaneously at 21 timestamps, so that we can hopefully say if it's really a particle flying by or noise, because the noise can be up to 75% of these hits, and it has to be removed before the further processing, so online. So it's described here some particular event which was measured, and so it's not a simulation. So we worked with real measured events. That's why we know that there is a large amount of electronics noise and some noise coming from the cosmic particles and so on. And since the upgraded experiment is still in build, we have a freedom to choose which electronics will be on which processing farm. That's why we could test on several CPUs and GPUs in order to find the good ones. So the labeling is important. So we have hits, as I say, in these TPCs. Here you see a picture of two big TPCs, and we have the left, this is the left and right one, the big ones. Then we have two smaller TPCs and some very vertex TPCs small. So, and on the left side, the gray picture is what we see in the measurement. And on the right side is a confusion matrix. So what we want is we want our algorithm to tell the yellow or orange left upper corner is the real signal, which we also identify as real signal. The right bottom corner is a real noise, which we hopefully identify as a real noise. But there is, of course, in real life, nothing is perfect. So sometimes there are false positives, which is something which is noise, but we identify as signal. And there is also false negatives, which is something we identified as noise, which is actual signal. And this is a lost signal. And we don't want to lose some important new particle. That's why we want to keep it as low as possible. So we want to reduce noise as much as possible, which means we need the green part of the confusion matrix as high as possible. And we want to lose as little signal as possible. So the red one has to be kept low. For this, also the performance is very important. And that's why we tested it on a typical CPU as the one which is probably going to be used, and a typical GPU, which is not there, maybe most powerful, but the one which is realistic. And the results for the performance times I will show you after I will describe which networks we actually used. So first of all, of course, we applied ResNet, because we know from the previous studies on different use cases that this network gives the best accuracy. And so we hoped to reduce the noise in most reliable way and also without overfit. Indeed, we managed to have 92% accuracy, and approximately also it means we can look at the confusion matrix. So bad labeled as bad is the green, it's almost 90%. So we can remove 90% of noise. And the red is in this particular network is 5.5%. So, and that we can still tune, but order of magnitude 5%. So 5% of signal we lose, 90% of noise is removed. So the accuracy is good. And the question is the generalizability, for example, that we tested. Why? Because we have trained on one part of the detector, one of the TPCs, and then tested it on the measurements from the other part of the detector, other device, other TPC, which is standing 2 meters away and in a different magnetic field. And we have lost only 1%. So it means the validation is very good. So we can trust this 92, 91% accuracy. So our second exercise was we wanted to understand what was the reason for this good accuracy. Why the network was able to identify noise where physicists cannot by just looking at the signal. So, okay, maybe a very well-trained physicist can do it, but not so fast. And so we have exercise by building a 2-neuron network. It's extremely small, of course. It's not going to perform as well as a deep learning, but we already got 89% accuracy. So the idea was this network, if only 2 neurons already knows something, it can remove 87% of noise. Of course, it loses 8% of signal, but it's just an academic exercise so that we wanted to know what it bases its decision on. And then one of our students has built the weights of the network for all input parameters. And if you look at this 3-dimensional plot, it's difficult to see, but we can rotate it. And then one can notice that in the center, the appearance of signal in the center of the actual center of the cluster is, of course, indicative that it's a real signal and not noise. That's logical. That's why the weights are positive. And off-center, it should be negative, but not in the corners. In the corners, it seems to be more or less around 0. So it's not important for the decision what is going on in the corners of this input data. Why is that? And we understood that it's because of causality, because the particles fly by, and of course they can hit several parts of the detector and leave traces in different paths, but not faster than light. And that's why we have a cross pattern here, where we see that the weights are negative of the peak if 2 paths fire exactly simultaneously with the same timestamp. It means the particle traveled faster than light, or if some particles suddenly stopped and started firing in the same path all the time, which is not possible because the particles fly with very high speed. So the network learned these very similar considerations, and already that leads to 87% of the accuracy. So we decided that we don't need the full ResNet, and we can concentrate on the full ResNet on the 2 dimensions, and we can concentrate only on this cross pattern of the input data. And then we have built an architecture which is tuned to these physics considerations. And I will show you why we did it, because of the performance, of course. So it's a convolutional network, but only built on the splitted input, which is on the cross pattern, and then combined for the decision without any more mixing the information from these 2 sides of the cross. So we call it splitted architecture. And the splitted architecture gives 92 also approximately % accuracy. It can remove even more noise than ResNet, 91%, and it loses 7% of the real. So, of course, it's not as big as ResNet. Now we can go to the main part. The main part is the performance, and does it really make sense to buy expensive GPUs? So, Simple Final, the last network in the list, is very fast, but it's, of course, not performing with the demanded accuracy the collaboration needs. So then we can concentrate on the split architecture and ResNet. The split architecture gives higher noise reduction, has less parameters, but has a little bit higher false negatives. And the split architecture performs on CPU within the limit of 3 seconds, but on the border of it. But ResNet lies out of it. Prediction time is above 20 seconds per event, because event has a lot of actual individual decisions, and that is not usable by the collaboration. On the other hand, if we not run on CPUs, but on GPUs, then we suddenly see that the network ResNet, which has 100,000 parameters, it's gigantic, it can run within 1 second. And the simplest split network also needs 0.3 seconds. So it shows that such architectures of convolutional networks, and especially this ResNet, which is split in blocks, it is very, very effectively parallelizable on a GPU. So if I was making a decision, then I would say, let's not lose any data. Let's take the best architecture, which is ResNet, and buy some GPUs. So if we have 100 GPUs, we can do online analysis of this experiment. Now, of course, it's not my decision, it's the decision of the collaboration. This is first of all. And I don't want to sound only optimistic. Let's put a grain of salt. A grain of salt is that GPUs are producing a lot of heat. So they are needing more energy, and that's why 100 GPUs in one room, which has to be near the experiment, will just heat up, turn too much, and they say that is not safe for the electronics, it will just burn. So I am too much theorist to know all these details, but our task was to analyze different machine learning methods and different architectures and to give all the information about the performance, about the possible noise reduction, possible speed and lost efficiency, the lost signal, and then the experimental collaboration as a whole can make a decision. We plan also, of course, to analyze which particular 5% of the data we lose, how this efficiency is depending on mass and momentum of these particles is very important in order to be able to compensate for this loss. And while this is in progress, when it's done, then it will be part of the actual run. And so I know it was a little bit heterogeneous presentation, but the main message I want to say is that deep and very deep learning is possible and useful, but has to be done with care. And if I want to use the best architecture, then I also need GPUs, because 100,000 parameters on a chip on a CPU will just take 20-something seconds per decision. So that is my message here. And I thank you very much for your attention. And I congratulate CPU Days with the 10th anniversary. Happy birthday and many, many more to come.
Okay, thank you very much, Olena. It was a very interesting talk. And I found it very homogeneously from this perspective where we are.
Thank you.
From HEP and the GPUs. You immediately got a question from Gabor. Gabor, are you online? Maybe not. The question is, you can see the question in the chat box. Can you see it?
For that, I have to change a view. Wait.
Yeah, please. Okay, maybe I can read.
Can you read it, please?
Could you elaborate on how the causality appears in the DL structure?
Can you please repeat?
Could you elaborate on how the causality appears on the DL structure?
Okay, I understand. Yes, thank you. Very good question. Indeed, this causality, that was for me very amazing. So it's a very simple network, 2 neurons. And so input is 21 times 11 matrix of numbers. And so these, there's like 200 numbers, are entering 2 neurons. So we have like 400 numbers which are processed. And so we have then looked at all weights. The weights can be plotted on this 3-dimensional plot. And if a weight is positive, it means the network learned that this number, the bigger the number in this point in the matrix, the bigger the probability that it's signal. So that can be done online. There is such great service, weights and biases. It can feed hyperparameters and plot for you, for example, all your weights. But for the complicated network, we have so many millions of weights that this plot will not be understandable for a human, for me. And now as a human, I was trying to understand this plot, which seemed to have a structure. So this peak in the center. You mean how in this split network? Yeah, okay. So, but let me finish. So this peak in the center was expected. And the cross comes from the causality. And the split architecture, that's a different story. So the simple architecture learned causality just from looking at the examples. I didn't teach it explicitly. I didn't tell it, look, that the particle doesn't move too fast or it doesn't move too slow. The network just looked at the examples and noticed if something is too fast or too slow, then it's noise. And then for the split, we helped. We said, don't look at the corners. So we cut away the corners from our input and didn't even show it. So effectively, we just made a network which looks at the input from this band and from this band. And one arm of this split was analyzing only the dependence on the timestamp, and the other arm analyzed only the dependence on the pad number. So one was looking that not two pads fired simultaneously, and the other was looking that not one particle was always hitting the same pad. And we didn't tell it also to look at this particular functionality, it learned it also. But because we prepared the input in such a way, by cutting away the non-important information, it could learn the causality by itself, very good, and it had more parameters than a simple neuron. Two neurons, it had more than 400 parameters, it had 4,000 parameters. That's why it could learn the causality even more detailed and even something additional to causality. So because it's a convolution also, it was combining the information from different pads together and from different timestamps together. I don't know if it answers your question. Can you give me feedback, please?
I think I got it, but maybe we can answer in the. Yeah.
Thank you.
Any further questions from Tony? Yeah.
So you have demonstrated how important the architecture is. Do you plan to do it somehow systematically to scan over all of the possible or reasonable architectures? Maybe, so you have shown three types and vastly different performance, so to say, in terms of number of parameters. So maybe I don't know. So how to proceed, how to exploit this knowledge.
So thank you for your question. Yeah, actually, yes. This was a relatively short presentation of work of 1 year in several centers. So in Frankfurt, and we have 2 centers in Poland, and in Gießen also my group a little bit helped. So the thing is that we, of course, tried much more architectures than I presented here. This is already a crystallization. So first step, although I, as a believer in deep learning, could say from beginning that convolutional will work better, but people tried dense networks, principal component analysis, normal decision trees, boosted decision trees, random decision trees, all possible decision trees, which are very, very fast. But my problem with decision trees, they overfit. They are just not generalizable. So we tried also pre-processing the data, so feature engineering also, of course. People tried first looking at what would be some interesting combination of inputs and then putting it in. So we tried many different things. And also what we did systematically, of course, the hyperparameters tuning was done systematically. And then we understood that if we want to tune on accuracy and want to have the highest noise reduction with the smallest loss of signal, then ResNet wins. And we don't need to go super deep, 3 blocks of 3 layers. That was enough. More didn't bring much and only made it slower. But ResNet is slow. So as I said, if we could just have enough GPUs and cool them, that's not maybe doable right now, but that would solve the problem. Then the next step was that the collaboration said, no, we need it faster and we need it cooler and maybe it should run on CPUs. And that's when we started thinking, wait a moment, do we really need 100,000 parameters? It seems to be stupid to just trust it, that it found a global minimum. And that's why we found a split architecture by looking at the limit of the biggest network, which works very well, and the smallest, these 2 neurons. And then we found this middle way. And I, from my side, formulated for the collaboration like this. These are the 3 best choices for you, choose one. But behind the doors, we tried another hundreds. And maybe in the end, we will take the gradient boosted decision trees, who knows, if we will understand that the efficiency. So the problem with decision trees is they don't generalize and they also lose more data. They lose maybe 12% of signal. But if we find out that these 12% are not the interesting ones, let's put it so, then it's okay. So that's the problems which people have in real life when we don't have infinite information.
Thank you.
Mm-hmm.
Okay, thank you very much. Olena, one quick question from my side. So, how could you improve the?
Sorry, it's echo.
So, how could you improve the efficiency of the SHINE experiment at the moment? So, I mean, can we see larger amount of higher statistic data soon or now?
Yeah. Yes. Thank you. So. This is still going to take some time. So in simulations, of course, first of all, in simulations, we will see where we lose the data. And the noise approximately now is at the low energy of the collision, and argon cadmium small systems, there we have more noise in comparison because we have less signal. So there we have like up to 3/4 is noise. And if we remove 90% of it, that means we remove 76% of points which we need to combine into tracks. So you understand instantly that the speed up of tracking is by a factor of infinity. I tried to calculate this factor, my computer said it's infinity. So the combinatorics just improves so much that we will be maybe even able to do tracking online. And that is even necessary because after the upgrade, so approximately it was planned next year to start data taking if God helps with Corona and so on. So the idea is that the NA61 changed the electronics, readout electronics, and did other also upgrades, in particular forward detector. And so they will be able to run at much higher luminosities and much higher event rates than before. But that's only possible if on our side, also in the software side, we will be able to analyze it so fast. And a little bit of advertisement here. Let's say 1.5 years ago, it was not looking good. It was looking that with the traditional tracking, for example, and noise reduction calibration, the maximum speed up we could get, for example, is a factor of 10, and we needed this factor of 1,000. But now with machine learning, if we will convince that we understand the efficiency and so on, and we really use it, then it's done. It's realistic. We are under 3 seconds per event per node, and it's online. And so we can really do all the noise reduction and even maybe tracking online. So that's the holy grail is reached. I'm really optimistic. So I think in this case, the upgrade will work, and the NA61 will have a event rate approximately factor of 100 more than before. And we cannot now tell you, for example, that the omega C will be measured or not. That is too early to tell.
Okay, thank you very much. So let's thanks all the speakers for the morning session, and let's come back to the original stage here. So thank you, Olena. So we are here at the end, and maybe ask Gabor to turn the camera to the organizers, and the Balázs is also here. All the Balázs are here. So let me make a couple of final words. That this was the 10th GPU day, so we are getting old. You can see my white bird. When we started, it was still brown, so I got also just a few words on the statistics of this event. So we had 83 registered participants and 20 talks with 23 speakers, which I think is a very good number, taking into account that we have this funny times. But we could make it in I hope we could make it in COVID safe here with 10 people locally. We still kept up the traditions with we have about 50 academic participants, 24 students, and 10 industrial partners. So I would like to thank all the speakers and all the participants, and I would like to ask my colleagues to come here to the stage. We can see ourselves over there, so and you can turn to the camera like this. Okay, so Balázs, Gábor. So I would like to really thank you all for the help you supported. You provided support during the conference. Everybody had to be taken into account in this case because these online events are much more complicated sometimes than the real one, and you have to act very quickly. So thank you guys very much. And we would like to wish everybody a very nice days and times, and hopefully we can meet in the next year somewhere, sometimes at the 11th time, hopefully without COVID. And thank you very much, and see you guys.
Thank you very much.
Happy birthday.
Take care, Olena. Olena, you missed the Hungarian food, but
Yeah, I really miss it. I miss it so much. I was really counting on that.
Okay, best wishes you and your family.
Best wishes. Köszi szépen.